my name is Vib. I'm here representing Shield AI. And today I'll be talking about how we make porting autonomy to new platforms quickly and safely. So a bit about me. I've been at Shield for about 8 years now. I joined on the perception team working on state estimation and mapping. And over time, I took on more systems and technical leadership roles. And eventually, I became the director of engineering for strategic projects, where I look at bringing in new technologies and new partnerships to help improve the autonomy developer experience. A little bit about Shield. So we've been around for about a decade now, and we've had a consistent mission the entire time. Our mission is to protect service members and civilians with intelligent systems. And we do that by providing autonomous software and hardware to enable warfighters with critical information so they can act anywhere at any time. We started in the early days with Nova 1 and Nova 2, doing indoor exploration to help support building clearance. But as the nature of warfare evolved and grew, we climbed the aviation food chain with VBAT, our medium segment vertical takeoff and landing system for large-scale reconnaissance over land or over water. We also put reinforcement-trained behaviors onto fighter jets to improve their combat ability. As we scaled our software to these platforms, we saw the real power of autonomy in this space and started partnering with many other companies to put Hivemind on their systems. Over the past few years, we have put Hivemind on over 15 different platforms. And now we took all that experience and lessons that we learned along the way and distilled it into an enterprise solution that can help others put autonomy on their own platforms. And that's the Hivemind SDK. And today, I'll be talking a little bit about particular components of that help make porting autonomy fast and safe. I'll do a quick overview of the product and then go into a few case studies to highlight that. So the enterprise solution is formed of 4 major components. EdgeOS is our foundational middleware for all of our platforms. It's built on C++ to be predictable, robust, scalable, and performant for the edge. On top of EdgeOS is Pilot, our catalog of perception and cognition modules. These help accelerate the development of new capabilities by providing an extensible starting point. And to refine that Pilot, we have Forge, our autonomy development factory. This includes tools like scalable simulation, scenario-based testing, and a large-scale analysis and testing. This is to understand how your pilot will perform in many different kinds of cases. And lastly, we have Commander. This is a human interface to the autonomy stack. This also includes services for integration with other parties, third parties, but also mission planning tools to help translate user intent into autonomous behavior. The 2 aspects of the stack that I want to talk about today is Pilot and Forge. And so first, I'll hit upon Pilot. When thinking about how to port autonomy to different systems, you want to start isolating different elements of the autonomy stack to things that are portable, or that are naturally portable, or in things that are very specific to a particular platform. Autonomy is not monolithic. And we want to create an architectural separation between what we call platform autonomy and mission autonomy. So platform autonomy deals with more of the foundational functions that are critical for basic operations. Things like sensor drivers, motor controllers, very specific to that platform. Mission autonomy deals with more of the goal-directed behavior. Things like multi-agent coordination, object tracking and detection, the higher level functions. This separation not only makes it easy to understand what is portable, but it's also important for software assurance. We fly on very expensive and critical systems that require very strict certification for the software that runs on them. These are standards like DO 178C or Military Handbook 516C, and they have very strict requirements. Things like running on a single thread, no GPU access, no dynamic memory, fully deterministic operations, things that modern autonomous software doesn't really want to comply with. In order to move forward here, we want to relegate some of those safety-critical functionality to the platform autonomy, allow the mission autonomy to use more of those advanced new concepts, but wrap it all in a framework that allows and guarantees the overall system is still safe. That framework is called runtime assurance, and we'll talk about that in the 3rd case study. While the SDK looks to support all parts of the autonomy stack, Pilot primarily deals with mission autonomy because it is more portable. And so let's look a little bit deeper into Pilot. To introduce that, here is our common reference architecture. This is our starting point for every autonomous system that we build within Shield AI. It has the traditional decomposition of autonomy into the perception, cognition, and action steps. EdgeOS creates that abstraction layer. It's the middleware to the platform. And all these components are provided within the SDK as they are. What's unique here is the extensibility thanks to EdgeOS's plugin-like system called mixins that allow users to extend these closed source elements with their own user functionality. These are things like adding a new factor type to the state estimation for the factor graph solver, or adding a new cost function for the task planning inside of cognition. It could also be in the action space, adding a new motion model to help translate some of the outputs of cognition into platform-specific commands. To help refine that pilot, we have Forge, which is that autonomy development factory. And here's a traditional Forge development workflow. You get requirements for what your autonomy must be able to do. You go through the development cycle to find and create that autonomy, the software, and you go into the testing phase. You design a scenario to understand, to set up this test for which your autonomy is going to run. You set up the mission with the goals of sending the goals to the autonomy stack, and you start working in simulation, where you do sim testing, collect the data, do analysis and evaluation. And once you iterate in simulation a few times, you move on to flight tests, where we have two goals. One is to close that sim to real gap by making sure your simulation matches the flight test you collected, and to actually directly refine the autonomy itself. Here's the first few phases of that within our Forge portal, our UI for creating scenarios and mission planning. So here I'm creating a scenario by placing entities into the San Diego Bay. Boats that have predefined waypoints. I can also change initial conditions such as the wind, weather, time of day, any number of things. Once I do that, I go into the mission planning phase where I put the Hivemind-powered agents into the environment and set up a mission for them to accomplish. Once I finish doing the mission plan, I go into the setting up the test case, where here I'm going to call out all the analyzers that I want to run on this. So this will automatically extract a lot of the metrics that I want from the flight test data so that I can eventually look at it and do levy pass-fail metrics. So here I'm setting up that evaluation criteria to be automatic so that I can set up n number of simulations and see a summary of all of those, whether they pass or fail in those criteria very, very quickly. So now I'm going to go into our case studies. The first one I'm going to talk about is how do we port to helicopters? How do we take a system that has predominantly flown on quadrotors and fixed wings and move to a new platform? This was in partnership with Airbus. Our goal was to put Hivemind on the MQ-72C Lakota platform. Our long-term goal is to do large-scale autonomous transport logistics in contested spaces. That generally means that you have no communications and no GPS. Our near-term goal for this was to do integration with this platform and do safe launch and recovery with a single system. So let's look at how we did that with our stack. So we start, as always, with the common reference architecture, the starting point for all of our autonomy software applications. And we look at the modifications that we made to enable this system. So first, on the sensor side, doing sensor selection, we know that we have to do a safe landing. To do that, we need to be able to detect what is below us and to determine a safe landing zone and routing ourselves there. So we added a bottom-facing LiDAR and cameras. This affects the state estimation stack, the perception stack, in a few ways. One, we added into the state estimation system visual inertial factors for the cameras to do eventually doing GPS-denied operations. On the mapping side, we want to create a reference with LiDAR data so we know how to operate within that and find a safe landing zone. On the action side, we want to be able to translate the cognition output into platform-specific commands. This particular platform had a few modes of control. One was waypoints. So this is just altitude, latitude, longitude commands. This would work well if you have GPS or doing simple operations. However, it doesn't really give you fine-grained control. So we chose the alternative method, which is a modified heading, speed, altitude commands, which is essentially equates to position and velocity set points. So with this architecture, we went into the refining phase. So this is kind of what that looks like within that Forge ecosystem. So there's a couple of things to call out here. So one is that there's an Unreal Engine-based image generator that's coming with the SDK that provides photorealistic camera data for training purposes. We also integrated an external physics simulator for dynamics of the helicopter. It's also thanks to Forge's extensibility and ability to integrate with different simulators. With that, we iterated in simulation, found our interface to the platform, refined it, and went to flight tests really quickly. We did a couple flight tests to ensure that the sim matched the real-world data and modify the parameters to make them look really good. Because we know we have to do GPS-denied navigation, we started collecting real-world data using a surrogate platform, but with the real downward-facing camera, and started training our visual inertial odometry algorithms on that. That all culminated into the right-hand side here. You see a depiction of a real flight test on a real helicopter, where we did an autonomous takeoff, went through a few flight test cards, and landed. And this is showing the Foxglove map panel with some annotations on there to highlight some aspects of that flight. And here's a video of this in action, showing the Airbus Lakota platform doing an autonomous takeoff and land. And one of the really impressive parts of this was the speed in which this happened. This did not take months or years. This integration happened within a few weeks from when they started this project to when we started flying and doing successful integrations and flight tests. In this next case study, I want to talk about heterogeneous search. So in addition to working on new platforms, I want to talk about how we can take advantage of that common reference architecture to build complex multi-agent teaming capabilities. The problem we're trying to solve here is how do we do surveillance of a region of interest and provide real-time information about that area to an operator that is decently far away. We are operating in contested environments where we have degraded communication, which means that cellular networks or long-range radios simply don't work. Agents are only able to talk together when they're in very close proximity. In order to solve this, we use a team of systems that have different roles. Some agents are tasked to do search of that area, and other agents are tasked to position themselves in a way to be able to communicate that information back to the operator, forming a communication bridge. So let's look at how we do that within our common reference architecture. So we'll dig into the cognition stack to be able to understand this. And here's this expanded version shown above. All of these are edgeOS modules that are running on the edge of every system with unique responsibilities. On the input side, we have that overall mission of understanding what's happening in that region of interest and getting that information real time. So the executive mission planner decomposes that mission into a set of tasks, which sends that to the multi-agent executive manager, which will then, in a pseudo-centralized manner, decide which agent does which task and sends that to the single agent executive manager to execute that task by taking through a behavior tree. There's other supporting elements here. One is the condition manager, which is acting like a watchdog that looks for conditions like low fuel to alert the single agent executive manager for any failures. As I mentioned, the network is not always consistent. Agents are going in and out of communication range. And so we have a communication graph manager that is actively monitoring the network conditions and alerting the team manager for any agents that go in and out of communication range. The team manager then is responsible for selecting the new leader for the system, and that leader is what decides and runs the multi-agent executive manager to do the task allocation. So all these were built up to handle cases like this, where we have a degraded comms environment. Extensibility is also here provided in a couple of different ways. One is setting up new tasks entirely, such as that communication bridge task, as well as heuristics that are used in the multi-agent executive manager to decide which agent does which task. Here's an example of this running in simulation with 6 agents, where 3 are doing the search and 3 are doing the comms bridge roles. You'll also see here that we have the Foxglove panel embedded within the Forge portal to provide a lot of real-time visibility. We have panels that look at the communication live to show how we're able to transmit throughout the whole mission. And we also have panels, all thanks to Foxglove's extensibility, that lets us introspect of the system in real time. Here we're seeing the edgeOS system with all the connections of all the different modules, and so you can see live also the parameters that were used to launch them, all while the simulation is running on the system, thanks again to Foxglove. Once the simulation has finished running, we go on to the analysis phase. And here is those analyzers that we set up earlier come into play, where it extracts these metrics automatically from the flight test data across all the different flights and levies the pass-fail metrics based on if it was successfully transmitting data the entire time, and then did it search the whole area as it was supposed to. This is all in simulation, and now we can see this happening in the real world. This is a flight test that we conducted recently with Shield AI hardware powered by Hivemind. We have 4 flying agents, where 2 are tasked with doing the search of the area, and 2 are tasked with playing the communication bridge. In addition to these 4 agents that are flying, we have 3 additional agents on the ground. We also ported Hivemind to these rovers within a few weeks to extend the communication range of the overall system. While these systems have some fixed tasks, they are able to be resilient to agent loss. So if any of these systems were to go down, the rest of the stack is able to adapt and still accomplish the overall goal of providing monitoring and reconnaissance for that region. And lastly, I want to talk about safe autonomy, or essentially, how do you iterate quickly on mission autonomy for platforms where assurance is required? We fly on expensive critical systems that have very strict requirements, as I mentioned before, things like DO 178C and Military Handbook 516Z. And I mentioned before that we relegated a lot of those safety critical aspects to the platform autonomy to let the mission autonomy be more flexible, but have that framework that made sure the overall system is still assured. And that framework is runtime assurance. And the details on this architecture are provided by another standard, ASTM F3269-21. The idea here is that you wrap this complex autonomy with simpler, but yet still assured modules. These modules are responsible for monitoring the output of the complex autonomy, detecting for any unexpected behavior, and intervening when required. This is how this fits into our overall stack. So this is the example of a flight compute unit. There are a few computers here. We have a mission computer that's running the mission autonomy, that's sending commands eventually to the platform autonomy side, the autopilot, or the flight control systems that is actually controlling the hardware. And in between this is our runtime assurance module. Now, we didn't want to solve this just once for one particular platform. We wanted to solve this and make it extensible so we can apply this to new platforms very easily. And we didn't want to just monitor for one kind of failure case. We want to be able to monitor for multiple kinds of failure case. And that's why it's the extensible multi-monitor runtime assurance system. So to get a sense of what it is internally, here's the next level diagram. You have sensor data coming in, going into what we call the integrity manager. This block is responsible for doing the monitor and detect aspect of that runtime assurance system. It has a few helper functions, like a map manager or a trajectory manager. The map manager can load a static digital terrain elevation map to understand where the ground is at different points in space. And the trajectory manager has platform-specific parameters that understands where the aircraft will be if you forward project the current trajectory. With that, you have an extensible set of monitors. Here is an example of a GCAS monitor, the ground collision avoidance system, that uses both the map manager and trajectory manager. But here you can add additional helper functions and additional monitors for extensibility. And the integrity manager is responsible for detecting any failures of the current trajectory or current output from autonomy and alerting the RTA switch. And the RTA switch is what's responsible for doing the intervention, the actual switch from one autonomy to the next. Generally, the Hivemind pilot will be going into the RTA switch and flowing directly into the autopilot, but when required, it will intervene and switch the commands. So here's an example of a flight test where we have Hivemind in control while the border of the video is in blue. We have purposely caused it to go downward. And when RTA takes over, the border of the video will turn green to show that RTA has detected, intervened, and saved the aircraft from a crash. You can also see in the Foxglove panel on the left-hand side where the altitude is shown in blue, and the vertical bar represents when RTA has taken over. In the future, we're going to add more kinds of monitors, but this is a start. So in this talk, I covered how we ported autonomy to different platforms very quickly, thanks to that common reference architecture and the built-in extensibility of EdgeOS. How we created resilient multi-agent autonomy that can handle network changes, and how we can iterate quickly and deploy safely on these systems using runtime assurance. Thanks.